So when the question is, will a precipitate form, we have to find Q. We'll be doing that a lot this hour. Most of the hour is going to be spent with that. So that's the second type of problem that we have. We've got solids trying to dissolve, find the solubility. We have, will a precipitate form, will it go back the other way? The last type of problem we're going to just get a snapshot of before we leave today, and that is, it's similar to what you read about last night. If you have something that's not very soluble, what can we do to make it more soluble? One of the things is what we read about last night. You'd add acid, and as long as the anion is basic, then that would get it to dissolve. And then there's another way that we can make things dissolve that wouldn't otherwise dissolve. We'll see what that's called a complex ion. Okay. Now I have a new type of problem for you. This one we did yesterday too. Will a precipitate form? This is still the same question. Will a precipitate form? But it goes one more step. What will the concentration of one of the ions be after the precipitation happens? Now, if you're one that likes to write out the problems, this is going to take you a little bit of time. It's kind of wordy and lots of sig figs in there. So we'll wait for you impatiently.
So we have to know what forms, right?
Yes. And sometimes the problem gives it away, like it did in this problem. It tells you what form because it gives you the KSP.
Will it always?
Not always, no. But a lot of times it will.
And how are we to go about finding what forms then?
You have the KSP table, so you have to look up what's insoluble. Or know the solubility rules. I have some things written underneath the shade. There's not going to be any room really to write out anything. So I'm going to put the chemical equation up here. I mentioned this yesterday. Don't forget when you're writing the chemical equation, even though you don't want to because you have ion concentrations. Yes, I know the ions are the reactant, but write it always with the solid on the left and then the ions on the right. You're going to see when you start doing these problems on your own, you're not going to want to do that. You're going to say, okay, I have ions here, those are the reactants. I know, I get it. But always write it like this. The precipitate, AgIO3, even though we don't have any to start with, is what we put on the left, and then silver ions and IO3. IO3 we haven't seen before. You may have never seen that in your life. It's very similar to chlorine. Chlorine is ClO3. IO3 is iodate.
What's its use?
We'll actually use it in a lab that we do in the next chapter. It's used for redox reactions. So what is this problem? Remember also, when we're combining solutions together, when we write the initial concentrations, we always use the solution formula. That's easy to forget to do too. So we don't just automatically go over there and write Ag is 0.002. It's not right. It gets diluted. Now, take a look. This one is nice because the volume just doubles for each solution. So the concentrations get cut in half. So the silver is going to be half of what it was, 0.0 mega. I'm going to start an ice table, at least. I want to show you what happens with this. The silver concentration is 0.001 molar. It got cut in half. The iodate ion concentration, it started at 0.01, that gets cut in half to 0.005. So we have initial concentrations of these two. The first thing that we're going to do is determine, is a precipitate going to be, is it going to shift to the left? Well, that's where we need to find Q and see if it's greater than K. The Q value over to the side here will come up with Q equals 0.001 times 0.005. What does that give us? 1 times 10 to the negative third times 5 times 10 to the negative third gives us 5 times 10 to the negative sixth. And if it helps you, just estimate the Q value, because we're talking about just comparing whether Q is greater than or less than K. So 10 to the negative sixth, the K value here is 10 to the negative eighth. So what's bigger, Q or K?
K is.
No,
The bigger is that one.
the bigger number. What's the bigger number? 10 to the negative 6 is bigger than 10 to the negative 8. Yes? So Q is bigger than K. Therefore, the reaction is going to shift to the left. The reaction shifts left. I have a couple of guidelines for you on this one. There's going to be two things that we're going to have to do. Anytime you need to find the concentration of something after a precipitation happens, the first thing you want to do is, I want you to assume that it goes all the way to the left as far as it can, which means that one of these two is going to run out. Go ahead and run it right out. Go to 0 for one of the reacting things. So assume the reaction goes to completion. So the reaction is going to do this. It's going to go to the left. The smaller amount is the silver. So it can only go as far to the left as what the silver allows, because that's the smaller amount. So that's going to go down by 0.001. And then therefore it will be 0. That's what I mean by going to completion. Now the iodate is not going to run out because it's an excess. So it's going to go down by the same amount that the silver went down, 0.001. Now when that happens, the reaction is going to the left. It's going to make some of this solid. So what we would observe is we combine these two solutions. They're going to be two clear solutions. And then we combine them. We'll see cloudiness. The solid will be made. It's going to get all cloudy, and then eventually it will settle down to the bottom. But as those go to the left, when that goes down by 0.001, this one will go up by 0.001. Now that is a solid, so it doesn't really have a concentration, but just know that some of the solid is going to be made. Now what has happened is that the silver is now gone. It has all gotten used up. We can't leave it that way though. In fact, the question is, what is the equilibrium concentration of silver? You can't say that it's 0. It's not 0, because you can't have anything with a concentration of 0 at equilibrium. Right? Everything has to have some value. So what we have to do then is step number 2, and again, I'm sorry about the wordiness of this. What we're going to do is assume it goes all the way to the left, but then it can't stay that way because something's going to be 0. Then we're going to have it drift back to the right. The reason that we do that is it seems a little bit intimidating at first, but it's not bad. This makes our math much easier. The math is super easy as long as you do this. If you just try to go to the left until it gets to equilibrium, the math winds up being a disaster. You're going to have 10 to a certain power. You're not going to get something accurate. Just do it this way. So go ahead and take a moment and write that down, and I'll walk you through what that looks like. Both ions. You'll have to find both. It says usually one would be an excess. Yeah, I'll show you what it is. Okay, are you good with what you're writing? Here's what I mean by this. We wind up having two different changes. So normally we have an ice table in which you have the initial concentration, and then there's a change, it goes one way or the other, and then we get to equilibrium. In this case, though, we're going to have two different changes. We're going to have the complete precipitation, as much as will happen, to completion. And then it's got to drift back, so it's got to have another change. So that looks like this. It's going to, now that there's some solid there, we're going to go down by some amount x from the solid as it shifts back to the right. And this side is going to go up by some amount x. We're going to see how much it goes back to the right. That allows us to know what the concentrations are. So now at equilibrium, we have a solid on the left that has no concentration. The silver ion, it was that. It totally got depleted, so it's gone to 0. And then we have added x back to it. So that's going to just have the value x. And this one on the right, it went from 0.005 down to 0.004 when we subtracted the 1. And then it's going up by x too. So it's 0.004 plus x. Does that make sense? It started at 0.005, it went down by 0.001, now it's 0.004. And then we've added also x to it, because the reaction had to shift back to the right. Now, this makes the math super easy. Let's take a look at the math on it. The KSP, which is given to us, 3 times 10 to the negative 8, equals the products, x times 0.004 plus x, over the reactant, which is just a solid. And that's it. Solve for x. The question was, what is the concentration of silver? That's that value. When we solve for x, we have it. Now, can we neglect that plus x term? We can. We can neglect it. Because x is going to be really small. You can see the k value is really small. So that means it only shifts to the right a little tiny bit. Even though 0.004 is not real big, the x term is going to be negligible compared to that. So neglect the plus x term, and now the x value, finding that is really easy. Oops. What's that? Mika, you're doing great.
Thank you. There's a glare.
So the big difference here, when you need to find the concentration after the reaction happens, what we need to do is make an ice table that has two changes in it. So rather than calling it an ice table, we're going to call it an ice table. See the difference?
Why can't we call it an icy table?
Call it icy if you want to. Yep.
Why?
I like to honor both sides of the Mason-Dixon line. So yeah, we have ice tables and we have ice tables.
How does
So-
that, how, where do you get that?
Don't ask any questions. That's what we'll do. So we've gone through one. I kind of went very slowly, deliberately slow. Let's try another one where we'll go a little bit faster. You'll see that we do the exact same thing. These two steps, though, this is only what you're going to use when you're asked for the final concentration of something after a precipitation. Whether we have two. It's got to go all the way that way and then just a little bit back the other way. Again, the reason that we do that is to make the math much simpler. I mean, this is a really simple math problem. We don't have even any x squared terms. That x has been neglected, so you just divide out the 0.004 and we have it. So let's try one more. A solution is prepared by mixing 75 ml of barium chloride with 125 ml of potassium sulfate. Jazz?
You said you had to divide the 0.04.
Both sides, yeah. So you just solve for x. And when you get x, that's it. It's done. Now, Mika, I don't need to go to the board anymore. Should we just put it back here?
Okay.
So you don't have to fiddle with it? Thank you. I lost my equilibrium sign. So the writer of this problem was kind. They also told us what the precipitate was going to be. That just saves us from having to figure it out. They gave us the KSP value of barium sulfate. That's going to be the precipitate. Okay, so I'll give you a flash for this one. The chemical equation for this one is barium sulfate yields barium ion plus sulfate ion. It's the same kind of thing. We're asked for final concentration. This time they want the concentration of both barium and sulfate. So we have to come up with the initial concentration of barium and sulfate. Once again, remember, they're being diluted, so make sure you have the dilute concentrations on here. The barium goes down to 0.0075. Is that right? 0.0075? And then the sulfate goes down to 0.025. Now, before we do anything else, we need to check Q. Remember, determine if the reaction actually goes to the right. So that's finding the Q value. Now, you can always just estimate the Q. You just need to know whether Q is bigger or less than K. So I would say you don't have to grab your calculator and multiply those two. Just estimate it. This is 10 to the negative third. This is 10 to the negative second power. So 10 to the negative third times 10 to the negative second is 10 to the negative fifth. How does that compare to 10 to the negative ninth? Is Q bigger than K? Yeah, Q is a lot bigger than K. So it's going to shift to the left. Yeah, and so I'm just, so in our notes that we acknowledge that we checked the Q value, we can confirm that the reaction is going to shift left. This is going to become cloudy with a precipitate in there because the barium sulfate is going to be big. Okay, so we're going to assume this thing goes to the left, and we're going to assume it goes to completion. So the barium is going to run out first. That's a smaller amount. It's going to be 0.0075 down. And so the sulfate goes down by 0.0075. Now, this is another problem where we've been a little bit spoiled. All the coefficients are 1s. That doesn't last forever, so enjoy it. So when that happens, when it goes to the right, the barium is going to all be used up. This goes up by 0.0075. And then we have to have it drift back to the right. So we'll have, again, our ah statement. As it goes back to the right, the barium sulfate is going to go back and slightly dissolve. As it does that, the barium goes up by 1 and by x, and the sulfate goes up by x. So then at equilibrium, this doesn't have a concentration because it's a solid. The barium was at 0, and then it increases by x, so it's just x. And then the sulfate, 0.025 minus 0.0075 is 0.0175. Yes. Plus x. questions about that? What we've done so far? Okay, so now we just have to do the math on it, which is pretty simple. KSP equals 1.5 times 10 to the negative 9. And that's x times 0.0175 plus x. Can we neglect the plus x in that quantity? Yep, x is small. Way smaller than that. So yeah, that little two change technique does allow us to have a very easy calculation at the end. Anybody have any questions or comments about this? The next one I'm going to ask you to try. It's going to be one that's similar, and I'll just leave you alone and have you try it. You ready for it? Try this one. I warned you that your luck was going to run out with all one coefficients. This one doesn't have all ones. you get a value for x. Is it, I can't remember what it is now. 2 times 10 to the negative 7th? Is that right? Let's see. The ASP is 6.4 times 10 to the negative 9. X times 0.055 plus 2x. Now, if you did it right, then you have it set up like this and you remembered to square that second term. That's the biggest mistake I've seen today. So what you didn't do? Yeah, so don't forget about squaring that one. Watch out for those coefficients. So, yeah, 6.4 times 10 to the negative 9 divided by 0.055 squared. We can neglect that 2x term. And we have 2 times 10 to the negative 6, not negative 7. Is that what you got? So this is the concentration of magnesium. And then the fluoride ion is just this thing, the 0.055. Because that number is tiny, it doesn't add anything to 0.055, even if you multiply it by 2. Raj? Oh, is that what I got?
Yeah, it should be.
Sorry, I said 6, I think, and then I wrote 7. Sorry. Okay. Take a look at the exercises in the book, which will keep you busy this weekend. Do everything up to the section that says complex ion equilibria. We're going to have to talk about that on Monday. I have enough time. I just want to show it to you today with a very quick little introduction, and then we'll just wait until Monday to go over it. But when you get to the second page of the homework problems, there's going to be a section that says precipitation conditions. Take a look at what they're asking you to do. Number 47 and 48, that's just finding the concentration with the common ion effect. The common ion effect. See, it says in number 47, we're adding zinc sulfide to a solution that already has zinc in it. That's the common ion effect. And then same thing with number 48. 48 is the same thing. You already have some. Oh, I hope you don't get that one. That looks like it's hard. Number 49 and 50. Will a precipitate form? Oh, we've done those. Just find Q. If Q is greater than K, then it's yes. If Q is less than K, it's a no. Don't just say, oh, I got a 50-50 chance. I'll just say yes to all of them. Number 51 and 52, same thing. Will a precipitate form? Will that precipitate? That's a question there. Will cerium iodate precipitate? So yeah, just find Q for those. Then we get to number 53, and from those, calculate the final concentrations. That's why we have to use the AS table. And come up with the concentration at the end. Now in 53 they weren't very nice to you because they even asked you to find the concentration of the spectators at equilibrium. So there's a little bit more to find there. And then 54, we just did that one, barium and sulfate. 55, we did that one, silver and iodate. 56, that one we didn't do yet, but it's the same kind of thing. You're given the amount of starting ions and then find what the final concentrations are. Then 57, what's the minimum concentration that causes precipitation? We did one of those yesterday. So yeah, these you'll be able to do all of them. Okay, so we've done lots of problems in which we've had to find out what the solubility of a solid is. We've done lots of problems where we are given just ions that are mixed together and determine whether they'll make a precipitate, whether Q is greater than K. The last thing in the chapter is what you read about. If you have something that's not very soluble in water, can you get it to dissolve by doing something else? Like two things. Number one, add an acid to it. That's what our reading assignment was. If we add an acid, if the anion is basic, then it'll cause it to dissolve. The other thing that we can do, and by the way, in my presentation here, not assuming that we did a reading quiz on this, I did have a couple of slides about what pH does to solubility. The big thing here, and this is what you read about last night, what you want to remember is if your anion is basic, then it will dissolve better in acid. If the anion is neutral, it doesn't do any good to put it in acid. It's going to dissolve the same as it would in pure water. Then I gave a little exercise. Let's see if we learned anything from the reading quiz. For each set, like for these 3 compounds, would any of these dissolve better in acid than in pure water?
The first one. No.
Yeah, the first one. Because the F negative ion is basic. HF is a weak acid, therefore F negative is basic. That's the conjugate of a strong, that's the conjugate of a strong. They would not dissolve better in basic. In acid. This one would though. Silver fluoride would, because the fluoride ion is basic. What about in this set? Lead hydroxide and lead chloride. Would either of those dissolve better in base? Let's say it again.
PbOH2.
Yeah, this one dissolves better in acid because it's a base. Yeah, you got the hydroxide ion. And then finally, between these two, do either of those dissolve better in acid? The second one does, yeah. That's the conjugate of a strong acid. That's not basic. That is basic, so that would dissolve better in acid. So yeah, there's some questions like that in the exercises. Then, this just an example. Oh, don't look at that.
That was just very.
The last thing, and it looks scarier than it really is. You can also get something to dissolve if it's a transition metal ion. If you have transition metal ion in a compound that's just not dissolving, but you need it to dissolve, you can make what we call a complex ion with it. This is only going to apply for transition metals. You don't need to write this down. We'll write it down on Monday. A transition metal ion, I'm going to use a word that we probably haven't used since the first week of school. The word is orbital. Remember what orbitals are?
Yes.
Yeah.
Orbitals are around an atom. They're the little regions that have room for 2 electrons. 2 electrons go into each orbital. The S sublevel has 1 orbital. It's got room for 2 electrons. The P has 3 orbitals. It's got room for 6 electrons.
1, 3, 5,
2 each.
7.
Yeah. Yeah. Ds have 5 orbitals like that. Now, transition metals, this is only going to happen with transition metals. The main group elements like sodium, potassium, barium, calcium, they don't make complex ions ever. The transition metal ions have d orbitals. They have a more complex electron arrangement, so they have these empty d orbitals. If you have one of these transition metal ions, it's got to be an ion too. It can't be neutral. It's got to be an ion, because it'll be attracted to something that has a lone pair. A small atom, molecule, or ion that has a lone pair on it would be attracted to it, and it'll actually stick to it. Now there is a name that we give to that small molecule that has a lone pair. We call that a ligand. I know the picture is scary. I want you to just take a look at it. You don't need to write anything down. What happens here is, this is our copper ion. Copper is a transition metal. So when copper makes a positive 2 ion, it's got some empty orbitals around it. Now what you see is there's 4 ammonia molecules. Ammonia is NH3. So N in ammonia has a lone pair on it. That lone pair is a little negative cloud on the molecule, and that negative cloud is attracted to the positive 2 copper. So what happens is that lone pair goes in, and it actually winds up occupying the empty orbital on the copper ion. Now that can happen with 4 ammonia molecules on the same copper ion. That makes this thing what we call a complex ion. It was an ion, the copper is right there in the middle, that was attached to by 4 ammonia molecules, and the whole thing still has a positive 2 charge. Because the copper was a positive 2, and the ammonias are all neutral. So it has made a bond, yet it's still an ion. Therefore, we call it a complex ion. Now, this thing turns out to be very soluble. So when you have like copper hydroxide that just is very stubborn about dissolving, you can either add acid to it to get it to dissolve with the hydroxide, or you can try to flood the molecule, flood the solution with ammonia molecules, and the ammonia winds up attaching to the copper, and this is very, very soluble. Now I'm going to demonstrate on Monday several things that are insoluble in water, yet we can make them make them complex ions, and it just dissolves them beautifully. It's pretty neat. Wait till Monday to see that. But that's what complex ions are about. You're going to see that it only happens with transition metals when they're ions, and then some small thing with a lone pair is going to come in and attach to it. You are the quietest that I think I've said that before to you. That you boys, some days I get you where you're just really tired.
It's Friday.
I'm paying attention.
Now was preoccupied with something, and Thamana wasn't
Thamana's
here,
just
so
like-
yeah, we missed you.
I mean,
Izzy, second
I wanna-
hour. I know you're watching too. We missed you too. Have a nice weekend.